by thanking the organizing committee of Advice 2010, and it's a privilege to share with you some of my working experiences with swarm intelligence and biomimicry, that means mimicking the nature, learning from nature for solving nearly intractable computational problems like those arising in the fields of this slideshow is actually concentrated to problems those arise in the field of swarm robotics. That's why the name is of this kind, a conceptual journey from insects to robots. So this is by myself and Triveni Prasad Banerjee, who is my PhD student. Things that I intend to cover in this show is an introduction to particle swarm optimization, which is a very recent and relevant swarm intelligence technique. Applications of PSO, which is a short form of particle swarm optimization, to mobile robot path planning, navigation, and cooperative task performance. Then a short introduction to bacterial foraging optimization, where we learn how to seek for the optimal points from the behavior of Escherichia coli bacteria that live in our intestines. Then a mathematical model for BFO, and a scheme for adapting the chemotactic step size. Chemotaxis I will come later. That is a technique that the bacteria use to go to the regions which are enriched with chemicals that are essential for their neutral system. Applications of BFOA to swarm robotics. We intend to cover these topics, obviously if the time permits. So I begin with a very natural question that comes up: what is optimization? Optimization is actually the art of obtaining best policies to satisfy certain objectives, at the same time satisfying fixed requirements. These fixed requirements may be imposed in terms of constraints to the variables that we optimize. In a very crude sense, optimization means you have a function of certain variables and you want to find out the globally maximum or minimum points of that functional landscape. That is basically the optimization. But the problem is very much complicated due to several factors. First one is already mentioned in this classical definition by Baroness Gottfried: fixed requirements. Maybe there may be certain relations between the variables which have to be maintained. For example, I may take a function f of x1 comma x2, which may be, say, x1 squared plus x2 squared. This has to be minimized under the condition that e to the power x1 sine x2 plus cos x2 by x1 is less than equals to 0.1. So this is a very bad kind of nonlinear constraint which has to be maintained, maintaining which the first function has to be optimized. So this is an example of an unconstrained optimization. Maximize z is a function of two variables, so we all know all these things. So I don't go for much time on these slides. It's a minimization of a multivariable function, and this approach is the most classical approach for numerical optimization. It is called gradient descent algorithm or steepest descent algorithm, where actually this is the actual recursive equation of gradient descent. As you can see, these are bar symbols, which have been, I think, converted into something else in this equation editor. This is x bar n plus 1. F of x bar is the actual function we want to optimize. X bar is a parameter vector. X bar n plus 1 is the value of x bar in the n plus 1th iteration. X bar n is the old value of x bar. We start with a gauged solution x bar 0 and then go on improving that solution using different technique. The technique for steepest descent is that this del grad of f of x bar is a gradient vector, and we move along the gradient vector in steps of mu. Mu is the size. This is a very classical optimization technique, and the gradient vector is nothing but a vector whose components are the partial derivatives of the function small f. So this way we go on. This is a pictorial representation. Again, all these are displaced maybe due to the mismatch of PowerPoint versions. Actually, this is a humanoid agent which is a trial solution and which should have been standing over here at this point. This is a trial or gaze point. This is the functional surface. This function is called sphere function. Sphere function because this function has the mathematical form f of x1 comma x2 equal to x1 square plus x2 square, just like that. And this plot is this, along this axis we have plotted x1, along this axis we have plotted x2, and along this perpendicular axis we have plotted f of x1 comma x2. So this is a three-dimensional visualization of a two-dimensional function. And an agent is a part of a software program which is designated to do certain things that it can do. In software terminology nowadays, agent is a universal term which is used to designate virus as well as some kind of trial solution which can have a dynamics to move on a conceptual functional landscape like this. Agent has a very popular synonym which is called avatar. So this is an agent, search agent we better say. It starts from here and it goes a step down along this negative gradient. This is the gradient direction. Gradient is basically tangent drawn to this functional landscape. So it moves over here, then it moves over here, then it moves over here, until the gradient becomes parallel to this x1, x2 plane. As soon as the gradient becomes parallel to the x1, x2 plane, values of all del f, del x's become 0. So the gradient vector there basically becomes a null vector. And if you look at this equation, once this vector is 0, there is no movement of the agent because x bar n plus 1 is equal to x bar m. So this should work finely only if at all points of the functional surface we can draw tangents. That means only if the function is continuous and differentiable. But reality is far crude from that. What about these kind of functions? Actually, gradient descent algorithm will fail for many complicated functions. Some of the examples you can see here. This is called Ackley's function in 2 dimensions. Again, along this axis we plot f of x1 comma x2, and you can see the landscape is riddled with multiple local optima. All of these local optima are very narrow, ridge type of things. And if a search agent gets trapped in any one such local optima, that means its gradient value will also be 0 at any points like this. But at all these points, it cannot move from there, it cannot escape. That is what we call trapping in a local optima. These local optimas are dangerous for gradient descent to work. This is a function whose landscape looks like a crushed paper, you know. And this function is riddled with noise. Noise means maybe f of some f of x bar plus a random quantity. That random quantity may change with iterations. That means it's like you have expanded a big bed cover, and below that you have switched on a table fan. So what happens? On the bed cover there will be waves. Similarly, these kind of functions have wavy surfaces. The maxima minima positions either roam, that means start traveling over the functional landscape, or they may even change. The maxima may get converted into a minima and vice versa. So some of the functions are not differentiable. So what will we do for handling this kind of functions? The modern approach to numerical optimization of these kind of functions, these functions actually appear in multiple domains of knowledge, diverse domains of science and technology. These functions may be squared difference between a desired response from a system and its actual response. That is an engineering design typically. These functions may correspond to say side lobe level and null control in antenna array design. They may correspond to something else in other domains. So in fact, ranging from social sciences up to space technology, that's a vast bandwidth area in science and technology, optimization problems are everywhere, in every corner. And mostly, the design objectives of engineering systems are modeled by such kind of functions of vectors, multiple parameter vectors, and the modern approach is multi-agent optimization, which is a parallel optimization, where on this functional landscape, instead of starting with a single gauged or trial solution, we start with multiple solutions together. These are humanoid agents which embody multiple trial solutions. Each solution is capable of moving. That means there is a dynamics by which we can change the location of these solutions. Our objective is to conquer this highest peak, which corresponds to the global optima of this search space. So we need to define a rule of the game following which if the agents move, then after some time this kind of a situation should arise. that most of the agents are near the global optima while the best agent conquers the big. That is what we expect from a good optimization algorithm. And it should also be robust enough to handle many different kinds of functions. That is what we expect from a black box optimizer. Swarm intelligence, these are the traits of swarm intelligence. Swarm, this term refers to a collection or group of living creatures which individually are very less capable, but when they are in a group, they can show you remarkably intelligent activities. For example, before the beginning of winter, you must have seen long queues of ants are moving from your kitchen to some hole in your garden maybe, carrying, each ant is carrying small food grains, small sugar cubes maybe with it. Each ant, every ant is nearly blind. It cannot see beyond 1 or 2 centimeters of radius. So, but the queue of ant is a remarkable thing to observe. That queue is moving from your kitchen to the hole in the garden, following a shortest path. That's very interesting. And even if you intercept the path with a long rod or something, they will go round through the rod, following again a shortest path. The path is robust. If you try to disturb their flow, they will not be disturbed. They actually communicate with each other using a chemical substance which is called pheromone. It's a kind of hormone. This technique, this ant moving technology has inspired the communication engineers to build certain routing techniques in VLSI layouts and also for mobile networks. And there is a dedicated subject today which is called ACO or ant colony optimization. Similarly, if you have seen the swarm of migratory birds, school of fishes, if you have seen the National Geographic channel, there they may show you all these things. Migratory birds do a great path optimization technique. They fly thousands of miles maybe from one continent to another, and each year they fly through the same route, come to the same place to lay eggs, to breed, etc. And then again they return back with their newborn members. So, swarm intelligence is an upcoming branch of computer science where we want to imitate these kind of natural creatures which do great things in solving their problems, and we imitate them to solve intractable engineering optimization problems that are our problems basically. So, swarm intelligence in a nutshell, it means dumb things when put together work very brilliantly. That is what is the main theme of swarm intelligence. These are just some slides. It's a flock of migratory birds. You can see they actually fly forming a V pattern. This is a school of fish. This school of fish search for food below sea water, and very quickly, following certain strategies, they avoid the attack of big fishes like sharks and other predator kind of fishes. This is a wasp made, this is a nest for wasps and honeybees. And you can see this pattern is not at all random. There are many facilities in these are actually small rooms in which there are facilities for keeping eggs at a particular temperature. This is fully engineering. If you look at this kind of homes that they made for themselves, this is quite remarkable. I think even beavers also. Beavers make homes which a part of which is above the water and a part of which is below the water in some pond or lake. And the below the water part is storage for their foods in winter, etc., when they don't have time for hunting. So these engineering things are quite inherent into these natural creatures. Basically, I would like to introduce this particular algorithm which was formulated in 1995 following the intelligent behavior of a school of fish or a flock of birds. It is called particle swarm optimization. This particular algorithm is befitting for real parameter optimization. Real parameter means all these search variables are real numbers. I was talking about ACO or ant colony optimization, which is basically dedicated towards discrete parameter optimization, which is used to find the shortest path between two nodes in a complicated graph, while particle swarm optimization is used to find the globally maximum or minimum value of a real function f of x bar. X bar is a real parameter vector. So here you see the basic philosophy of the algorithm has been outlined in this way. There are 3 jars of fruit juice, and this one is the biggest jar containing maximum amount of fruit juice, and there are bees flying over these jars. Obviously, if this situation occurs, if I put 3 jars here, I have already seen many bees outside. So if I put a big jar here, a small jar here, and another small jar there, etc. So what happens is, obviously the big jar gets much crowded with many number of bees, I think. Most of the bees will be attracted towards this big jar because it has large quantity of fruit juice. It has large face area where many bees can sit and simultaneously quench their thirst. So this big jar can correspond to the global optimal point of a function, which most of the search agents look for. Small jars are like local optima. When a new bee comes into this room, it's biologically significant that its velocity is influenced by 3 things. First one is its current direction of flow, because when the bee enters the room, it has an inertial velocity. It has a velocity for inertia. Then it is to some extent attracted by the jar which is nearest to it, nearest jar. And also, due to its observation power, it observes by hearing. It can hear the sound made by other bees which are crowding on the biggest fruit juice jar. So it will try to move simultaneously in these 3 directions. It will be attracted by these 3 directions, and its resultant velocity is shown by this red arrow. It's a compromise between these 3 efforts, actually. In case of particle swarm optimization, we start with a population of search agents which are called particles, and each particle is having a velocity vector associated with it. These yellow arrows are velocity vectors. This is a functional landscape. That means this is a plot of that f versus x1, x2 in 2 dimensions, obviously. Randomly scattered particles, and each particle is having a velocity. We expect that when the algorithm converges, convergence means most of the particles are near the global optima, the best particle should reach the peak. This is the situation after a few iterations that is expected, and the velocity of the particles are being modulated in each iteration following the same principle that I told you about the bees. Before going into the main equation, let me tell you, this is the locus of a particle. This may be the locus of a particle. A particle may fly along this path. While moving in this path, this is the best position found so far by a particle. This is the particle's own experienced best position. That means while moving in this path, at this position, the particle was nearest to this global minimum. This is the global minimum. This is the best position found by the entire swarm. Swarm means a group of particles are moving parallelly in this fitness landscape. So this is personal best, this is global best. There are neighborhoods that we can define. Every particle can have a neighborhood. Neighborhood is like this. Geographical neighborhood is like this. These 2 are nearest to this particle. Similarly, these 2 are nearest to this particle. These are the 2 neighborhoods of this and this particle. These neighborhoods may also have other particles common among themselves. There may be social neighborhoods like this. These social neighborhoods are defined based on certain criteria. These 2 particles which are not nearest to this one, but they are neighbor to this one. This is quite common from a sociological perspective. I may live at far north of a place, my uncle may live far south of the place, but we are neighbors socially. Or my other relatives may be scattered over the city, but we are obviously neighbors by society, sociological relation, I think. Similarly, these 2 are neighbors of this particle. This slide illustrates the basic philosophy of particle swarm optimization. At every iteration, we go on updating the velocity of a particle and updating the position of a particle following the same strategy that I was telling while showing the figure of bees. Let me explain it in a little bit general tone. That is, social grooming of human beings are also a compromise between 3-4 different tendencies. PSO was originated by Kennedy and Eberhard. Rassi Eberhard was an engineering professor in Purdue University, US, and Kennedy was a social scientist or sociologist from Labor Research Institute of USA. They joined their hands together to mimic nature and come up with this algorithm. So obviously this algorithm has a sociological motivation behind it. For example, suppose Mr. X has a small boy who goes for cricket coaching, and Mr. X wants that his boy should be very good cricketer in future, maybe another Sachin Tendulkar or something. So his boy goes to the cricket coaching every day in the afternoon, and in the cricket coaching there are other neighboring boys who come for learning cricket. This small boy, suppose his name is Vijay or something, Vijay, he tries to imitate the best cricketer he has come across so far in his own experience. That is, this small boy has not got the chance to meet Sachin Tendulkar, but he has met another neighboring boy whose name is, say, Ajay, from his same locality, and that Ajay is a very good street cricketer. He is very efficient in breaking the window glasses of other people in the neighborhood. So Vijay tries to imitate Ajay, his strokes, his techniques of holding the bat, his techniques of striking the balls, etc. Everything. So Vijay tries to mimic. Also Vijay, in his TV set, he observes Sachin Tendulkar or other big cricketers like maybe Kapil Dev, Mahendra Singh Dhoni, all of them, and he tries to imitate the best one, who may be Sachin Tendulkar. He tries to imitate him. Sachin Tendulkar is the best cricketer from the entire community to which Vijay belongs. That is the community of Indians. Say, for example, there maybe argue about this, but let's take Sachin Tendulkar is the best cricketer of India. So obviously Vijay wants to imitate Sachin Tendulkar also. But then Vijay has his own limitations, his own muscular grips, his own nervous response. These things limit his capability. How fast he responds to an upcoming ball, that is limited by his brain activities, which are inherent. So Vijay's grooming is actually a compromise between 3 tendencies. One is his inertial limitations. One is his wanting to mimic Ajay, who is the personally met best cricketer in his neighborhood, and one is his attempts to mimic Sachin Tendulkar, who is the best cricketer from his entire community. So as a compromise between these 3 different tendencies, his grooming in cricket comes up with time. The same principle is actually followed in many other living societies, living creature societies, and that is imitated in particle swarm optimization. We see that this is an agent, search agent, whose dynamics we have to define. This search agent has 3 different directions to be attracted to. This is the globally best position found so far. This is marked by PGB. Actually, this position is nearest to this lowermost, not this. Due to the tilting of the functional landscape, it seems that this is a little bit higher. But this position is the best position found so far by all the particles in the swarm. This is the globally based particle. And this current agent is attracted towards the globally based particle by a quantity like this. This is the difference vector PGB minus XIT. XIT is the position of this particle at the tth time instant, tth iteration. This is the ith particle. PGB is the location of this. So this is a difference vector. This difference vector is multiplied by a random number between 0 to C2. This random number is having uniform distribution. So this C2 rand 0,1 PGB minus XIT is a randomly scaled attraction towards this position. Similarly, this is the position found so far by this agent. This agent have moved in a locus. In that locus, this position was the nearest to this globally best, to this actual optima actually. So this is the personal best position, PLB, and towards PLB, this is the term that corresponds to attraction towards PLB. C1 is another fixed number, and rand comma 0 comma 1 is a random number between 0 and 1. So this term corresponds to a random amplitude or step size between 0 and C1. PLB minus XIT is the random difference vector, and this VIT is its own inertial velocity from the last iteration. It is carrying its own inertia of motion. That velocity is VIT. So VIT plus 1, that is the velocity at the next instant, is a sum of three terms. First term is inertial velocity, scaled by some number phi, which is called inertia factor. The second term is a stochastic attraction towards the personal best position. The third term is another stochastic attraction towards the globally found best position. This way, at each instant, the velocity of each particle is modulated, changed, and the position of the particle is modulated by this equation. XIT plus 1 is the position of the particle at the next iteration. It is XIT plus VIT plus 1, which is the new velocity, into 1. 1 is the time instant gap between previous iteration and next iteration. So by this is actually x plus Vt, this kind of thing. T is 1 conceptually. We are talking about discrete time. So every particle trace, this is a continuation of the previous slide. Here I am, this is my inertial velocity, this is my best performance so far. This is called I proximity, how proximate I am to this personal best position. I try to move to some extent towards this, and then this is the best performance of my neighbors or my entire community. So I also try to, this is G proximity, therefore globally best proximity. I also try to move to some extent towards this, and this is my new position. This is how the dynamics of PSO goes on. This is the full algorithm. It starts from this initialized particles with random position and velocity. Fitness value is defined as how we measure how personal best position, globally best position. We measure it by putting the position vector of the particle in the function expression f. The function f of x bar is a scalar function of the vector x bar, and we see how much greater the value of the function or how much lower the value of the function. If we are dealing with a minimization problem, best position or better position corresponds to an x bar, which reduces the value of small f or the function to a large extent. Compare and update P-best and G-best refer to personal best and global best positions. We go on updating P-best and G-best, then if the stopping criteria is not met, we go on updating the velocity and position. Stopping criteria corresponds to either we can go on running this algorithm for a certain given number of generations that fit to the computational power of my computer, or we want to go to, suppose I want you to find out the minimum value of a function fx, and my tolerance limit is, I know the minima, if I know, if it is an engineering design problem, that is fx is a difference between the desired response and the actual response from an engineering system, then I know the actual optima is at 0. The actual optima must be at 0. It's a quadratic error response. In a neural network, it may be, some of you must have seen this, the difference between the actual response and the desired response, squared sum of that. But every time we cannot approach exact 0. So I may tell you, you stop iterating the algorithm as soon as we get 0.005 as the value of the function. So 0.005 is a very small number, and in many engineering design, we may not have the actual 0, but we may approach close to 0, which is sufficient for our purpose. So that is the stopping criteria. This was a very fantastic paper by Maurice Clark and James Kennedy, which explained why this principle or particle swarm optimization should work on different functions, why this algorithm at all can find the optima on the basis of algebra and complex calculus systems. This paper achieved the Outstanding Paper Award in TEC, stands for Transactions on Evolutionary Computing. It is the best journal in this area. Application areas of PSO are very vast. In very multidisciplinary areas, these are applied. 60 papers in different archival quality IEEE last 5 years. Major areas you can see: digital signal processing, robotics, wireless networking and mobile computing, bioinformatics, adaptive optimal control. Many different areas are there. Already IEEE has published 2 special issues on this PSO algorithm. I have just outlined the algorithm, but it has many other variants, many other implications associated with it. In this small talk, my basic objective is to provoke your aptitude or your maybe flair towards this particle swarm optimization, so that you can explore yourself what are there in store. Let me just illustrate a few. What is a robot? A robot is basically, put it very simply, it's a computing system fitted with limbs. The limbs can move it through. And robots are very useful in many applications. One example is garbage clearance from nuclear reactor plants. Inside a nuclear reactor plant, you cannot enter workers because there is a possibility of gamma radiation, being exposed to gamma radiation, which will create you bone cancer. So what we do is we basically put there swarms means groups of mobile robots which can go inside, clear the nuclear radioactive garbages, come outside, etc. Similarly, unmanned autonomous vehicles are nowadays used by even by DRDO. There are unmanned helicopters that fly over these big like areas like Kargil, Sandakphu, all these areas, glaciers. They observe whether there is any intrusion from Pakistan or something like that. So these things, these observations are done by unmanned autonomous helicopters, which are basically flying robots. So by general agreement, a robot is a programmable machine that imitates the actions or appearance of an intelligent creature, usually a human. These robots basically embody the final attempt to make a machine behave like human beings. So robots are built on multidisciplinary engineering systems, from computer science, from mechanical engineering, from electrical engineering, from electronics engineering. People must handshake to make effective humanoid robots. I don't go into much details about this. Robotic manipulators, these are some robotic manipulators which are robotic hands basically. These are 2 joints. This is like the elbow. This is a robotic hand. In fact, this robotic hand, if you program it properly, this hand is available in JU, if you program it properly, it can paint a figure on the blank canvas with one drawing brush. This is a mobile robot means types of robots, there are many kind of robots different. We use these robots very frequently. These are called Pioneer 2 mobile robots. It has 4 wheels and 2 grippers. The grippers can move like in this fashion. They have 2 degrees of freedom. And in between the grippers, it is carrying some Coca-Cola cans, as you can see. These are aerial robots. These are hexapod legged robots. These are underwater robots. They operate below the sea. They can be used for observance of the sea surface, below the sea surface. They can even measure the temperature of water below the sea level, how the plankton population is behaving, how the water current is behaving, all these they can measure. These robots are used by NASA for Mars exploration. It's a Land Rover system used for Mars exploration. We are not going into the detail. Path planning of mobile robot is a huge problem which requires most recent technologies to be addressed. Path planning means I switch on a mobile robot from here, it has to go to that door without colliding with any obstacle sitting here. Obstacles may be of 2 types. Either obstacles may be static, like this audience, you all are sitting steadily, you are not moving. But if it is a party going on in this room, people are dancing, and the robot has to carry a tray of, say, certain soft drinks, etc., from this position to that position without colliding with any dancing people, then it's a problem of dynamic path planning, where the obstacles are continually moving, intersecting the path of the robot. The robot has to track it. For tracking, for visualizing, actually as human beings, we do it inherently. We have no difficulty in doing this. So planning a collision-free path from one point to another is a very important problem. And as robot eyes, there are 2 things. For cheaper robots, they can use sonar. They can send out infrared radiations. That infrared radiation go and stuck in an obstacle, come back to the robot. From that, they can measure the time of flight, estimate the distance of the nearest obstacle. But that is for cheaper robot. That technology is very cheap. For costlier robots, which are used in intricate applications, we have digital cameras with pan and tilt fitted over the robot. If I go back to the previous slide, this is the robot eye. You can see it's a digital camera which can move in this fashion and also in this fashion. It has 4 degrees of freedom of movement. So this digital camera captures frames from the world it can see, from what lies before its lens. That captured images are processed in a very rapid rate. Those images are analyzed using computer algorithms, and from those images it estimates where is the nearest obstacle, in which direction to move to avoid collision, etc., etc. Swarm intelligence approach towards centralized path planning goes like this. This is the robot location. These are the obstacles. These are the directions in which the robot can move. And we define, I again don't go into the detail of this mathematics, but each robot has a processor, a hard disk associated with it. Robot means computer plus limbs. So in that processor, a small PSO with a small population runs, following which the robot moves on. It minimizes a function like this. In this function, these are the distances between the robot and the nearest obstacle. So the motors fitted with the robot generate torques in such a direction. These torques, what is the value of the torque? What is the value of the heading direction? These are the search variables that we want to optimize using PSO to avoid collision with the nearest obstacle and to also minimize the path between the current position and the goal position. So our objectives is, one objective is to avoid collision with the nearest obstacle. Another objective is to move a step forward to minimize the distance between the current position and the goal position. And our search variables are what should be the desired torque and what should be the desired heading direction in terms of angle theta and moving radius vector r. These we want to optimize. This is distributed path planning. This is the trajectory. The PSO started, these are static obstacles, and a robot starts from here, it has to go to here. The PSO initially started with a best path which was like this green dotted path. Finally, when the PSO converged, the path that was planned for the robot through this static world map of obstacles has been shown in this red path, which not only avoids the obstacles but also minimizes the distance traveled. This is very important because if the robot unnecessarily moves through large distances, its battery will be exhausted very fast. So for working better with low power, we need it avoids collision with the obstacles but move in a shortest path. These are some experiments these are some comparisons with existing algorithms. This is back propagation neural network trained robot system, which moves from this start position to this end position through these obstacles. This is SOFM. And if you look at these two figures, these are from the simulation window of Pioneer 2 mobile robot that I have shown you. If you look at these two windows and if you look at here, you see this is the PSO based single robot path planning. A single mobile robot is moving. It is not only avoiding the collision but also moving in a nearly straight path. That is, the distance of this path is shortest. These paths are carved, the distance is not shortest. How we evaluate the performance? We have 3 heuristics for evaluating how good a robot's path planning is. These are some examples on distributed path planning. The world map, when number of robots is 8, number of obstacles is 5. This is the final configuration for a world map. Each robot has to go from a starting position to a goal position. It's a group of robots moving through a group of obstacles. Distributed path planning means if the path of each robot is being optimized with a PSO. So if there are 8 robots, 8 particle populations are running and 8 different answers are generating from 8 PSO systems. That has been shown how the initial and final paths are moving. Cooperative task-driven robot behavior using PSO. This is another very interesting application. So we have a few papers that are coming in IEEE transactions on robotics and automation in this area, cooperative task performance. It means suppose there is a large box. That box has to be pushed from one starting end to a goal end. But the robots that we are using are very lightweight, short, small robots. So 3 or 4 robots should attack the box start applying force from different sides, and cooperatively they should carry the box from big trunk from one side of the room to the other side. That is another problem, where cooperatively the robots are moving, pushing a box from one side to another side. So here also these are the how particles are represented for each robot. This beta I is the angle, Fi is the force, Gi is the torque. While moving the trunk, the robots must not apply torque on it in such a way that if the trunk starts from here like this, when it appears on that door, it should not be here like this. If the robot pulls it down or pushes it up, then that is a bad thing as compared to what we need or expect from the algorithm. I'm again not showing all these things. This is a simulation. This round box is being pulled by 3 small robots. This is the trajectory, which is like this. It goes to the goal state. This is another example where a cubic box is being pushed by a group of 3 robots. This is the goal state. How the box is behaving in the midway, how it finally appears here. These are some experiments that we do in JU. Some experiments that are used for these papers. This is a small robot. It's a very cheap robot. It is moving on 2 wheels, and it's entering into a place which is obstructed from all sides using packing boxes, and it has to find, it is throwing infrared radiation to find, estimate the distance from the nearest obstacle, and it is generating the torques, etc. by using PSO assisted technology. So it is moving without colliding with any of the box. It has entered and it has to find. This is the first part. The second part is here. I think you can see this. It's moving and it will ultimately go out of this hexagonal cell which is full of obstacles. That is what we are doing here. So finally it comes out. That's the end of the video, I think. This is another example of how this is a robotic limb which puts something from a car box to another place. You can see how the grippers are coming, and for all these we need to calculate what is the force, what is the torque, how much it should rotate, etc. These calculations are being done by using this particle swarm kind of techniques. This is actually a sequence where we see that these 2 robots are working. This is a Waybot platform. Waybot is a very interesting software for especially those who want to do research on robotics but don't have enough infrastructure or funding. They can use this software medium for experimenting with robots. Waybots is the name of the simulation software package. The 2 robots are, their actual task is, these red things are actually ultrasonic sound sonar transducers. They are sending ultrasonic sound wave in here to estimate the distance of these red blocks. Their task is to pick them up and put them on this bench one after another in relay system. One robot carries this thing to a certain distance, then another robot carries it, relays the same thing, ultimately put them on this box. So last thing is bacterial foraging optimization is also a very interesting algorithm of recent time. It was by K.M. Pacino of Ohio State University, US. First, he laid the founding stone of bacterial foraging, where the behavior of Escherichia coli bacteria, which are actually responsible for creating colitis type of diseases, but their behavior is imitated to solve distributed and single optimization problems. Basically, foraging theory, foraging means searching for food, and every living organism, even we also continually search for, we don't search for food exactly, but we search for good salaries, etc., etc. We are also optimizing our gains in one way or the other. Animals search for and obtain nutrients to maximize E by T. E is the energy obtained per capital T second time. That is the basic objective of most of the animals. So foraging constraints are like physiology. Physiology means shape of his own body, etc. Predator-prey relation. In every ecosystem there may be some prey, there may be some predators. Environment for animals is continually being perturbed by human beings, by deforestation and so on. So these are constraints. Among following these constraints, the agent means the animal has to optimize its energy intake. So obviously the foraging strategies followed by the natural creatures lead to optimization. This optimization is necessary for their sustaining lives, and we are there to imitate these techniques to do certain things. Such foraging strategies use collective intelligence to find maximum amount of nutrients, avoid noxious substance, and predict predators. So a forager uses a searching strategy. These are the food patches, nutrient patches. These are the groups of predators. Predators may attack the forager. Predators are like large sharks which attack frequently the small groups of fish which are searching for or phytoplanktons. But their search is captured by this kind of large predator groups. So they have to, not only they have to find the food patches, but they also have to avoid the attack of such predators. So Escherichia coli, if you look at it very carefully, it has a long flagellum. It's a tail kind of thing, which is a biological motor, and it rotates in a very high speed. By rotation of this flagellum, it's a kind of propeller kind of thing that is fitted with all ships. This Escherichia coli bacteria moves forward. It has two kind of movements. One is swimming in the forward direction, one is tumbling, that means getting back in the back reverse direction. Sensors, actuators, controllers, and autonomous underwater vehicle. Nanotechnology's dream, that is the ultimate aim to follow this cell, the organism, this kind of activities that happen in this cell. Ultimate aim is to find small, very small, of the order of nanometer scale robots which can fight different diseases when put in our bloodstream. Exactly in that way the recent technologies are going for fighting cancerous tumors which are inside the body. People are planning to use such nanobots. These are called nanobots, which will mix with the bloodstream, go into the desired area, fight the cancerous cells, etc., etc. These are the ultimate dream of the upcoming century, I think. Chemotactic behavior means a bacterium naturally moves towards the direction in which it maximizes its chemotactic gradient. That means in which it can accumulate more nutrients, nutrient type of chemical substances. For doing this, these are the strategies that the bacterium follows. This is a functional landscape on which these bacteriums are acting as agents. A bacterial swarm foraging on a fitness landscape. There are four major steps. First one is chemotaxis, second one is reproduction. The bacterium population can create similar copies. Third one is elimination dispersal, fourth one is swarming. Using these four steps, the bacterial population finds out the peak of nutrients in its neighborhood, and this leads to the algorithm which is called bacterial foraging optimization algorithms. These are the four steps in the algorithm also. I am not going into the detail of these mathematical expressions, but I will show you some results. Swarming is also something by which a bacterial group keeps together. This is how BFOA working on the two-dimensional sphere function. This is the optima of a two-dimensional sphere function, and these parts of the cycles, these are called constant cost contours. They are the lines that corresponds to f of x1, x2 equal to constant. If the function is x1 square plus x2 square, then x1 square plus x2 square equal to constant. That yields the equation of a circle. So that's why these are the concentric circles. These are the trajectories of different bacteria. How over iteration, bacteria is the name here given to a search agent. In particle swarm optimization, we call the search agent a particle. Here we call it a bacterium. So these are the trajectories followed by the bacterium. Ultimately, all of them converge over here. That is shown in four different snapshots. What we did is, for the first time, is we analyzed the stability and convergence conditions of bacterial foraging optimization by deriving a dynamics like this. This VB corresponds to the velocity of the bacterium. Velocity in discrete time we define as xt plus 1 minus xt. Xt plus 1 is the next position, xt is the previous position. The time difference is 1. So that is how we define velocity. Velocity equation gives us the dynamics. On that dynamics, we use certain theorems from control theory. One of the theorem is called Lyapunov's stability criteria, or Lyapunov's stability theorem, which is very important. Using Lyapunov's theory, we have devised what are the necessary conditions for stability of the bacterium, what should be the parameters of the algorithm that guarantee convergence of the bacterium towards the desired optimal position. Also, there was a problem of oscillation. A bacterial population would oscillate around the optima continually if it could not have been properly perturbed with different other techniques. So, to get rid of that oscillation problem, we proposed an adaptive bacterial foraging technique. And this paper, it is not in press for so long, but it is already published in May 2009, IEEE TEC issue. This is another paper which addresses that problem and solves it and shows some applications to robotics. This is a chemotactic step size adaptation kind of thing. I am not again going into the detail. Application of BFOA have yielded these things: distributed intelligent control, swarm robotics, where a large group of robots are controlled, but only one BFOA should run. What I have shown you in the earlier slides, distributed path planning, there are multiple PSO populations are running on each robot, but in swarm robotics is such a field where a number of small robots will move into this room, but there is no central controller or central big computer which will control these robots, but each robot will have in its own processor a small optimization algorithm running. That is the basic objective of swarm robotics, and these robots should exchange data among themselves. This is like communication that appears between ants through pheromone. These robots should exchange pertinent data among themselves by wireless radio technologies. So for this, BFOA is a very important thing. Design of active power filters, pattern recognition, optimization of real power loss, voltage stability. These are power engineering problems basically. Learning and neural network problems are very prominent in this domain. Different IEEE transactions. Last 2 years, BFOA is very young. It originated in 2002 only. So now it is only being at its peak state. Everyone is using it. Vehicular swarms. This is an example of swarm robotics. The last example of my slideshow. I think I have already consumed much time. This is the goal. These are the obstacles. These are some small vehicular robots. Vehicular robots, I don't know you have seen in recent movies or not, small cars. They can move, or they can be moved using remotes also, or without remote also. A few small cars may be pushed into a room, they will move doing certain things. Vehicular robots are very favorite for certain groups of terrorists also. This can be moved into certain offices to blast the office, etc. They can carry bombs as well. They can act as remote controllers for bombs. So these are some certain vehicular robots which the objective is to avoid these obstacles and to reach the goal. Here it is moving. It's a MATLAB simulation where these small robots, I think these small robots are visible, they are moving, avoiding these obstacles and coming to the goal. This group is totally being controlled by using a bacterial foraging optimization strategy. And ultimately they have come over here. But the thing is, the swarming is not very good. Not everybody is properly converging to this, and also they are getting scattered out of the certain range from the goal. This we can mend or repair by using adaptive BFOA. The last slide is about that. Of RoboSwarm with adaptive BFOA is the variant that we proposed. Here we see that the swarming is in a much better thing. They are not getting trapped in this small. These are actually local optima. These are the position of the obstacles. They are not getting trapped into these obstacles. They are ultimately moving into this global optima, which is the goal actually here. Here the attainment of goal is like attaining the global optima, and here you can see the robot swarm is much compact. They are not scattered much. So this is how it works. So I think I have taken already much more amount of time than what was designated for me. So these are some important thrust areas in which many works are going on. These are the final trajectories of the robots, I think. And with this introduction to biomimicry and this fascinating area of robotic research, I would like all of you to apply all these algorithms in your own domain. You are experts of different areas. With this, I would like to conclude my talk just after this slide comes. Thank you.